to get onto today is to finish up this idea of cyclohexane. I will finish chapter 4 today. So the first exam is chapters 1 through 4, as it usually is. A lot of material, yes. Come and ask questions. I'm available this afternoon and tomorrow. Don't leave it to the last minute. And find out that axial is a problem. The fact that you put a large group in an axial position on a cyclohexane ring is usually a problem. And that's because you have interactions across the cycle. So I need to define this. Where does this 1,3 thing come from? Well, it comes from the fact that over on the right-hand side here, there's my number 1 atom. And 2, 3 atoms away, I have a second axial substituent. Now listen to this. You cannot have 1, 2 diaxial interactions. Why not? Because they're pointing in exactly the opposite directions when they are 1 and 2. It just doesn't make any sense. It's only when they're pointing either straight up above or straight down below that axial substituents can interact across the cycle and give you a problem. So that's the definition there. What we need to do today is to expand this into more complicated structures because, again, I've said we're leading to biology, to biochemistry, to engineering, stuff like that, much bigger subjects with much bigger molecules. You have to be comfortable with more substituents. Things like glucose has 5 substituents. Where do they go? Which is more stable? Which shape is more stable? And it's all based on these first simple principles. So what I've got here is a picture showing the first sort of example of stereoisomerism. Stereo just meaning space. If you wear headphones, hopefully if they're working, you're hearing in both ears. And, you know, the sound is engineered so that you have a stereo experience. Stereochemistry, which you may not have heard the term, is basically the projection of groups into space, away from a molecule. So we'll see that in certain instances, if groups are pointing in the same direction, we'll give that a name, we'll call it cis. And if groups are pointing in opposite directions, and they can't rotate, we'll call that a transisomer. So this is the first introduction to that, and all I talk about today is this idea of putting a second substituent on and talking about stabilities. So I can see here the chlorine is pointing up. Is that okay? It's pointing out of the plane towards you, and the methyl group is kind of dying away into the distance, which we use the dash to show, and that therefore is what we call the transisomer. What we'll need to do today, and you certainly will have to do on Friday, is to translate that sort of flat, not very descriptive depiction with a wedge and a dash into chair forms. And then talk about relative stabilities of chair forms. Which one is better, which one is worse, when you start to put groups on there. So it also requires some common sense. If you think about some of the things we've spoken about before, which is bigger, iodine or fluorine? Iodine, right? We dealt with that when we talked about acid-base chemistry and the size of the anion making a difference. So those same ideas will apply here, and you should have some idea of what's bigger. In this case, it's the methyl group that's bigger than a chlorine. And obviously a fluorine's bigger than a hydrogen. So that common sense stuff needs to come with you. You'll see now that we have 2 possibilities. Here we have the transisomer, in which the chlorine and the methyl group are pointing in opposite directions. Now, when you translate that into a depiction on the cyclohexane chair, you can do it in 2 different ways. And you can think about chlorine pointing up and chlorine and the methyl group pointing down. They are definitely pointing in opposite directions, yes? One's up and one's down. It can't be more clear than that. And this is one chair depiction. Now, the other chair depiction, which is related through a ring flip, has the chlorine pointing equatorial and the methyl group pointing equatorial. Now, which one of those 2 is better? The one on the right, because they're both equatorial and they're both avoiding 1,3 diaxial interactions. And I'll try to point out something here. If you build the models, which we've been doing in office hours, and plenty of people have shown up to get that advice, that methyl group looks like it's getting close to that hydrogen. It isn't. If you look at the model head on, it is pointing in opposite direction. It is not getting close. This is where experience comes from, and taking your time to learn this stuff thoroughly so that you don't get trapped with these ideas. This methyl and this hydrogen are not close to each other. Okay, this methyl group now is pointing out in this direction, the chlorine's pointing out in that direction. They're actually pointing away like that, right? They're not very close to each other at all. So this is much better than the one on the left by a long way. And we'll now say that the vast majority of these molecules will exist like this on the right, and very few, if any, will exist like this on the left. Now, we dealt with some numbers last time. We said that if you have a T-butyl group on there, it's 99.99% equatorial, and very little, if any, axial. You can imagine if you put more groups on there, they all want to be equatorial if they can. So you start to lead to this idea that the equilibrium favors one side completely, and the molecule just looks like one side, and there's none of the other conformation present. So ask questions today. Make sure we're okay with this. It's not just for this exam, it's for the future in terms of using it to be able to describe chemistry that's coming up. So trans basically means opposite direction, right? Transcontinental, across the continent, stuff like that. The cis isomers exemplified by this one. This is now a 1,3 isomer. We can see here that the ethyl group and the methyl group both have to be pointing down. you could draw this isomer with them both pointing up. As long as they're in the same relative orientation, pointing in the same direction, that's your cis isomer. So now we've taken the time to draw two at the bottom. We can see on the left a chair conformation in which both groups seem to be equatorial. That's fine. And on the right, they're both axial. And what we should be able to see now, I'm going to go hunt down my pencil because I've lost it. Where is it? Is that there's usually going to be one conformation that's overwhelmingly favored. Okay? Get rid of all this. Where's my pen gone? There it is. On my slide here, I want to point out on the flat picture, there's your problem. We use that symbol to show that problem. That's the issue. And don't forget that the way we draw these structures, we've sort of gone backwards and we've said, let's take out all the complexity. But you've got to remember that this is not just small. This is large. This is large. They get in each other's way. So once you get this, it's fairly obvious. Things want to be equatorial. If they happen to be axial, then put the phone down. The problem with this room is I can see exactly what you're doing underneath your desk. Don't do it again. You're out. We have a situation here where we have preferably equatorial, and we have equatorial, and here they're clashing. That's the big problem every time. So we'll start building some structures. I'm going to use the pen to try and draw this from scratch. I want to make sure that you understand this so that you don't necessarily memorize this stuff. You can actually do it from scratch. You can do it from first principles. So here we go. This is a transisomer. Is that okay? I have one group sticking up. I have one group sticking down. That is definitely a trans orientation. Now be very careful here. This cycle dictates a certain background to this. You cannot rotate around that cycle. If you try to rotate around these bonds in the cycle, you'll break the cycle. That's not allowed. So this group here is stuck on the opposite side of the molecule to that group. Absolutely. They are not going to be able to become cis. So these are different isomers, as you know, like a constitutional type isomer. I have now on the bottom two pictures. In this example, where we happen to have the trans 1,3, are we okay with where 1,3 comes from? That's the substitution pattern on the cyclohexane. We happen to have a trans 1,3 isomer. We're going to go in a minute and go systematically through all of them so you see where this comes from. But if I draw the pictures for this trans isomer, and I start off arbitrarily with this one on the left, and I put the ethyl group axial, we get a certain amount of instability because we get interactions across that cycle, which causes that. That's the issue. And if I go across and I do the ring flip through that process we talked about in detail on Monday, I now have to put the chlorine pointing down axial, and I have to put the ethyl pointing in the other direction. Now, people will say, well, why not just put your chlorine equatorial and put them both equatorial? What's the problem with that? That's not the trans isomer. That's the cis isomer. You can't change these things. We're not doing any chemistry here to change these things. It is stuck as being the trans isomer, so we're trying to deal with that. We can see here the chlorine's pointing down. You certainly have problems. Be prepared to do stuff like this. Show me where the problem is. Okay? The detail required here is pretty, you know, it's a high level. Be prepared to show me what a 1,3 diaxial interaction is so you understand it. You're not just memorizing stuff. That's a problem, but it doesn't seem to be as bad a problem as it was for the ethyl group. So what do you surmise from that? Which is bigger, the ethyl or the chlorine? The ethyl, right? There's the physical measurement that tells you that. So the molecule prefers to look like this on the right, even though, this is key, even though one of those groups has to go axial, because that's the identity of the molecule, the vast majority of them will look like that system on the right-hand side because you've got the smaller group axial. You have fewer problems when that happens. Okay? Busy couple of days coming up here. So what we start to do here is to, again, identify and define cis and trans, and talk about how you recognize these things. And then we go around the cycle. We do 1, 2, 1, 3, 1, 4. Why not 1, 5? It's the same as 1, 3, right? You're going to go around the cycle halfway and look at the relationships between groups at 1 and 2 and 1 and 3 and 1 and 4 from scratch. So we could draw this type of what we call a Howarth depiction to sort of show this for sure, that these two methyl groups are pointing up. They're on the same side. I could turn the molecule over and have the methyl groups pointing down. It's still the same molecule. They are still on the same side. It's still a cis isomer. Now on Friday, it's all about alkyl and alkanes, because we haven't done bromines, we haven't done iodines yet, we haven't done alkyl halides. So you'll see alkyl groups attached to these things, and your job is to decipher what's going on. We can see here trans is defined as being on opposite sides, and the point is you cannot do this. There is no interconversion between those molecules under regular conditions. Under normal laboratory conditions, that will not happen. So what we need to do here is to do this. And this is fun. If you start to understand this stuff, organic chemistry becomes very much manageable, and much more manageable than subjects like biology, because it's all the same stuff and you're just applying the same set of rules. So what I want to do here today with the pen is try and prove these statements from scratch by drawing these things. And I want to point out, because not everybody's in recitation, I want to point out how do you approach these things, how do you draw them, and how do you start to make things clear. Now I've got to grade 141 of these things over the weekend and get this back to you by Monday. And you'll find that this is kind of fun because people will draw the same thing different ways, but it's still the same thing. And my job is to try and interpret that, okay, and do it as quickly as I can, accurately. So I'm going to try and show you my sort of take on how this works. The statements here are to be proven. That's what I'm going to do here. Cis-1,2-dimethylcyclohexane is less stable than the transisomer. Okay, I can't remember that. This is why I like this subject. My memory is garbage. But I can prove things. It's like mathematics. I can prove the theorem, I can prove the equation, and away we go. If you understand how it's working, you don't have to memorize it, you just have to go and do the problem. So the statement is saying cis-1,2-dimethyl, could be di-anything, dimethylcyclohexane is less stable than the transisomer. We'll try and prove that in a second. We'll see now that cis-1,3 is more stable than the transisomer, and cis-1,4 is less stable than the transisomer. Now be very careful here. There are no shortcuts. The cis isomer isn't always worse than the transisomer. If you think about those two pictures at the top here, trying to prove how this is better to learn from scratch, what's the problem here? It looks like this and this seem to be getting close to each other, right? Maybe that's a problem. It looks like these two things seem to be getting away from each other. That seems like it might not be a problem. We have to prove it. Because again, those pictures are not adequate to explain the structure of the molecule. They exist as chairs. Maybe in chairs, this is better, and maybe in chairs, that is better. It is not immediately obvious from those pictures. We have to go through and prove this from scratch. So I have a blank slide. And please write this down as you go so you get some idea of how to do this, especially if you're not going to come to my office hours and you're not in recitation. So this is saying that cis-1,2-dimethylcyclohexane is less stable than its transisomer. We have to prove that. What's the first thing I do? I draw down some representation of the molecule I'm dealing with. So I've got a cyclohexane. First off, I'll start with that. Cis-1,2-dimethyl. I don't know, I like wedges. You could put dashes, it'll be the same thing right now. There's two alkyl groups, and that seems to be the cis isomer. Is that okay? Cis-1,2-dimethyl, that's the first thing I would do. And I'm trying to prove that that is less stable than this. So down below, I'll draw the transisomer. And the transisomer, it doesn't matter if I put a dash here or a dash at the top, as long as one of them is a wedge and one of them is a dash. It does not matter. After that, I need to start thinking about these cyclohexanes. And I'm typically going to draw two cyclohexane pictures so that I can show the relationship between them. Sometimes one is better than the other, sometimes they're the same. So I've got dimethyl here. And just for clarity, as a piece of advice, you start at one end. You start at either the left or the right. It does not matter. So, anybody. Do you want to start at the left or the right? Jordan, where do you want to start? The left, right? So I've got a situation here where I'm going to start on the left, and I need to make this cis. So I'm going to put this one pointing up. That's my first methyl group, just arbitrarily. You could choose down if you want, it does not matter. You will get to the same place. Now I'm thinking about cis-1,2. So I've got a situation here where I only have to concentrate on carbon 1 of the cycle and carbon 2 of the cycle. I don't care about everything else. It's a CH2 group. It's not playing any part in this system. If I need to make this cis, where do I put my methyl group? Sticking up axial or sticking out equatorial? Up axial. If we don't see that, we need to see it quickly. My methyl group has to be pointing up for this to be the cis molecule, because now they're both pointing in the same direction. So far, so good? Right, let's do a ring flip. This is where I asked you to practice, and hopefully we've done that. And let's see what the consequences are of doing that. We're going to drag this part of the molecule down. We're going to drag that part of the molecule up and see if it gets any better. Maybe it will, maybe it won't. That's what we're trying to prove. If I drag this thing up, where will this methyl group go in my other structure? Will it go axial or equatorial? It'll go axial. And my hydrogen, which was pointing down axial, will have to go out equatorial. That's that finished. Now, on this carbon, I still have to make an attempt to show that this thing is a tetrahedron, and I'm only dealing with 2 carbons here, I don't need to worry about the rest. I had a system in which the methyl group on the left was axial. Where will it be on my new picture? Equatorial. So it's going to go there. You don't have to be perfect at this. I'm not very good with the pen on the flat screen like that. It looks legible. I can read it, I guess. As long as I can read it. Yeah? That's the whole point of this, is clear communication. Now, let's look at that system. Is this good or bad? It's equatorial, so is it good or bad? It's good. What's this here? Axial. Is that good or bad? Okay, so I've got one that's okay, I've got one that's not so good. And they both happen to be the same group. Move over to the right. Is this good or bad? Bad. It's axial. What about down here? Good. What do you think the relative energies of those two pictures are? Equal. The same, because you have the same groups. So what would K be for that process? Well, not approximately, because it would be one, wouldn't it? You'd have 50% of each because they're both the same group. So that's the situation for that cis isomer. That's all you can do, is draw those pictures and explain that those two things are energetically equivalent. So let's go to the bottom one. Let's try and draw again 2 of these 6-membered rings. It does not matter which one you start with. That's part of the fun of grading this. Because I'm rushing to get through this. Equals. Everybody likes a wise guy, right? Anyway, we're now moving on to the second one. We're going to look at the situation with the transisomer. And I'm going to arbitrarily pick, I don't know, who wants what? Joe, what do you want, left or right this time? The right, why not? It's different. I need to deal with that. And I'm dealing with a 1,2 isomer. You can see the concentration required here. I need to deal with those 2 carbons. Now I'm looking at the transisomer. So, Erin, you want to go axial first or equatorial first? Axial, good idea. Doesn't really matter. There's one of my methyl groups pointing up, if you like. There's a hydrogen pointing down. Now, on this adjacent carbon, to make the transisomer, does the methyl group go down axial or out equatorial? It goes down, right, like that. Do we see any problems here? What is the relationship of those 2 groups? How are they pointing? They're both axial. That's awful. That's not good at all. So if we can do this ring flip and go over here, maybe it will get better. And it's going to be fairly obvious when you start to see these things. Drag that carbon down, drag this carbon up, do the ring flip. Where will the methyl group go here now? Equatorial. And the next one, where will the methyl group go? Equatorial. Now, this is that problem I just mentioned on the earlier slide. They are not far away from me. They are not right on top of each other. They are pointing like this. If you had a model in front of you, they're actually pointing in opposite directions. They're pointing away from each other. So that's not a problem. For this isomer, which picture do you prefer, left or right? The one on the right. Why? Because they're both the large groups are equatorial, and that gets rid of it what? 1,3 diaxial interactions. Look at the homeworks. Look at especially the answer keys from my previous exams. Look at the depth that's required for the answers. You're never going to get points for one word in my class. You're going to have to put something out. But neither do you have to write War and Peace, right? You do not have to write a novel for these things. Usually, a few words is enough. So we're done with that, right? So what do you think K for this is? Is it greater than 1 or less than 1? Greater than 1. We'd rather be over here on the right. So then we're trying to, deal with this statement down here. Cis 1,2 is less stable than the transisomer. Does that add up? Right? So of all of those 4 pictures, which is the best? Everything's equatorial. Great. Which of those are the worst? This one. Got to be very careful here. A lot of detail. So you can guarantee that all of these molecules in the transisomer case will look like that on the right, and very few, if any, will look like this on the left. So now you can make the statement, yeah, the cis isomer, which is the one above, is less stable. Why? Because one of the groups has to go axial. You cannot avoid that. And you prove it. That's all there is to it. Memorize it, good luck. You'll forget it within a few minutes. Understand it, you can do it forever. Everybody okay? Friday's going to be great. I love grading. It's going to be great. Okay, so there's that argument for the first one. Now we'll just move around. do the 1,3 isomer. So here it says cis-1,3-dimethylcyclohexane is more stable than the transisomer. Let's prove it. We can see here a cyclohexane, and we're keeping it simple so far with something like a methyl group, so cis-1,3. Who wants what? Jenna, what do you want? A wedge or a dash? Oh, why not? It's Wednesday. Put a dash right there. Now, to make it the cis isomer, does the next depiction have to be a wedge or a dash? Has to be a dash, and it has to be at 3 carbons. And I could do it over here, or I could do it over here. I'm right-handed, so I'm doing it over here. Fair enough? That looks like cis-1,3-dimethylcyclohexane. I hope it does. Now, to make it the trans isomer. What do you want to start with? Vince, what do you want to start with? Do you want to start with a wedge or a dash? Wrong. No, exactly. You can do whatever you want. You said wedge? Wedge. My point here is that somebody, your answer over here might look completely different to their answer over there, but it's the same answer. How is that possible? That's the nature of the game. You're looking at this molecule from different angles, getting the same molecule. So here we go. If I want to make this the trans isomer, Danielle, what is it going to be? Wedge or a dash? It certainly is. Now I have the setup. Now I'm ready to go. What I need to do now is draw my chairs and try and prove this from scratch. You can draw your left-hand chair first or your right-hand chair, does not matter. Completely up to you. I'm going to draw them like this because I like it like that. Fair enough? Now, do you want to start from the left or the right? Mark with a C. The other left or this left? I'm going to start here. Now, 1,3, just little bits of advice. If I go back over here and call that my 3 carbon at the back, that often leads to overlaps in the bonds and it gets confusing. So for clarity, I'm going to go here. That's my 1 and my 3. It does not matter which direction you go technically, but to be able to read it clearly, the front is always better. And if I do my ring flip, just to put my axes in, I need to be there, and I need to be there. 1 and 3. So let's start this off. I have a methyl group, which is a wedge. Stefan, what do you want? Do you want it up or down? First one. Make a decision, dude. Up, right. Okay, so let's call this up. Doesn't matter where you start. It's relative between the two pictures. That means my hydrogen's pointing down. I'm trying to draw the cis isomer. So as I go over here to finish this off, where does my methyl group go? Does it go equatorial or axial? It goes equatorial because then they'd both be pointing up. And that's fine. And quite often it just falls out. That's pretty good, right? That's pretty good, but we have to prove it. They're both equatorial. That's probably the best picture you'll get. Now, if we'd started differently, if somebody had started differently here, and we decided to go with the axial one first, we would find that, yes, we would get them both pointing up, okay, but they're both axial. So which is better of those two? The one on the left, by a lot. The one on the right has significant diaxial interactions, is not going to exist much at all. So I'm thinking this is good. Fair enough. What's K for that? If you just set it up like that for an equation. Is it less than 1 or greater than 1? Less than 1. There's more of the stuff on the left than there is on the right. So that's that done, finished. Down at the bottom, I have my 2 methyl groups. I need to show how this is going to set up. I need to draw my 2 chairs, make a reasonable attempt at doing this. And I have, again, 1, 3, so let's do that. And I have 1, 3 there, let's do that, and away we go. Okay. Brienne, up or down to start? Up. Let's go up. Let's go up over here, just for fun. An H over there. Now, this is the trans isomer. So when I draw my next methyl group on there, where does it go, axial or equatorial? It goes axial. It goes pointing down here. And all of a sudden, very quickly, we've got problems. Because this, by definition, is the trans isomer, and it can't have both groups equatorial. That would not then be the trans isomer. So I go and do my ring flip. Where does the methyl group go here when I do my ring flip? Does it go equatorial or axial? Equatorial. And H is sticking up. Now down here on the right-hand side with my 3 carbon, is my methyl group going to be axial or equatorial? Axial. It needs to change, okay? It needs to go axial to make that make sense. And I think I'm finished. This isn't difficult once you get into it. If you're still struggling with chapter 2, this is impossible. Hopefully you're not. Right, which is better, left or right, or about the same? They're the same, aren't they? Both have one methyl group equatorial, both have one methyl group axial. So what is K for this process? That's it for the breaking down of the problem into the subcomponents, so you can see what we're trying to get at. Now we need to reconcile this with the statements at the bottom. Cis-1,3-dimethylcyclohexane is more stable than the transisomer. Does that add up? The top picture, this molecule overall is more stable than the one below it. Does that add up? Yes. Why? Because both large groups can be equatorial. And very little, if any, will look like this on the right. It's going to look like this on the left, and that's by far the better of the two situations. Adds up, yeah? The isomer is better. Now, don't memorize this because you won't remember it. Okay? Practice it. Have a go at it. Anybody got any comments? Ashley, where are you? Say something. Fine. Okay, that's it. Fine. Anybody of our shy people at the back? Bleahu. Got any comments? I bet you will on Monday. In fact, I won't be here on Tuesday. I've got stuff to do. So, you know, Monday's a big day to get the exam back. Last one. Once you get this, it's pretty straightforward. Cis-1,4-dimethylcyclohexane is less stable than the transisomer. Okay, that means nothing to me until we prove it. Let's go for 1,4. Let's draw the cyclohexane out like this. Harley, do you want to start with a wedge or a dash? Wedge, why not? Do you want to start with a wedge at the bottom or the top? Isn't democracy great, hey? Right there, right? Yeah? And I'm drawing the cis isomer. So do I need a wedge or a dash next? I need a wedge. And it needs to be down there because that's 4 carbons away from where I started. That's my cis-1,4. Now, if I want to draw my trans, doesn't matter what I do. Paige, what do you want? A dash or a wedge? Do you want it top or bottom? So what's the next one going to be? A dash or a wedge? It's going to be a dash. That's what you do. That's how you start. So let's face it, Friday is a test of what I would like you to know so we can go do some chemistry. That's basically what it is. It's a spelling test. This is spelling. We haven't done much of any chemistry. There's only one chemical reaction on this test, which is acid-base chemistry. This is all physical ideas. So I'm going to start here. I want to draw some attempt at the cyclohexane. I'm going to do the opposite here to represent the ring flip. And I'm going to have a go at putting things in. Taylor, you want an axial or you want an equatorial to start with? Axial, right? So let's go for over here. Axial, methyl, H over there. Now, on the opposite side of the molecule, if this is the cis isomer, where does the methyl group go? Equatorial or axial? It goes equatorial. In order to be pointing above the plane of the molecule overall. So I do my ring flip. I get to concentrate on 1 and 4, so I just put my axes here. And see what I've done here? I've put my groups at the ends of the molecule so I can see them. I don't get any overlaps across the middle of the molecule. I can see it. It's easy to read. It's very clear-ish. If I drag this down on this side, where does the methyl group go, equatorial or axial? Equatorial. And my hydrogen goes there. And what happens to the other one on the other end? It goes axial. If you drag this up, that methyl group goes with it, and we get axial. Any comments? Do we like them? Is one better than the other? They're about the same. Same. So you've got a problem regardless of which one you look at. That's not great. So we go down to the bottom one. And I draw some cyclohexanes. And I'm going to start there and there because it's clear that way. Kayla the sneezer. You want to start with a wedge or a dash? You want to start with an axial or an equatorial? Axial. I'll have an axial, please, Alex. Right there. Okay. Now, on the other end of the molecule, it's trans. Am I pointing up or down? Down. So what's the orientation? Axial or equatorial? Axial. Looks like that. Good, bad, or ugly? Don't like that at all. What can it do to alleviate that problem? It can flip. So if it flips, this guy goes where? Axial or equatorial? Equatorial. And be very careful, folks. I have not turned my molecule at all. If you want to guarantee a way to go completely crazy on Friday, start turning your molecules all over the place. I've seen it. It's not fun. Keep your molecules simple. You're looking at an orientation, keep looking at the same orientation. Don't be turning the molecule here. In this example, all I'm doing is ring flipping. This comes down here, this comes up there. And on this carbon over here, Marissa, the midfielder, wherever you are, is this going to be equatorial or axial? Equatorial, certainly. Are you a midfielder? Defend, am I? I'm sorry. Okay, I get it right. I should know my football. Okay. Which of those two pictures is better? This one down here. Which is the best of the lot? This one down here. So all of your molecules of that isomer will look like that, where you have both big groups equatorial, no diaxial interactions. So does the statement at the bottom make sense? The cis isomer is less stable than the trans isomer. I think so. This is better. Why is the cis isomer less stable? Because one of the groups inevitably has to go axial, and you can't avoid that. Yeah? It's fun, this. So it's not physics, right? It's much better than physics. Or quant. Anybody want to say anything? Sarah? No, just the ones I'm focusing on. Okay, that's a good question. You will waste time. You do not have time to waste from now on in your lives. I don't care about those. I don't care about those, because guess what? When you do the flip, the hydrogen was equatorial, it went axial, the other one went equatorial. They're the same thing. It did not change. I'm interested in change. I'm looking at what has changed. So I don't really care about those other pieces. Anybody? Mr. Altawari, go ahead.
So changes from axial to equatorial, stay up.
It is. That's a good question, right? So if I've got an axial this in direction pointing up, and I go equatorial, it's still pointing up. Yeah? It's impossible to go the other direction. It's still going to end up pointing up like that. It's a good point. It's very much practice. You know, you practice this stuff, nothing difficult here. Difficult is exam 2. So moving along, the whole point of that story, that sort of attempt to show you how to draw these things and how to think about them, is to understand that on cycles, which are prevalent in pharmacy, medicine, biology, veterinary science, clinical laboratory science, engineering, just about everywhere you're interested in, 6-membered rings, 5-membered rings are really important. They are superstructures for bigger molecules, such as glucose. Polymeric glucose in starch, in cellulose, stuff like that. This is important. Okay? The fundamental ideas of molecular shape. And in this case, axial interactions are bad. Again, let me define this so we get this right. That's carbon 1, that's carbon 2, that's carbon 3. Both of them have an axial group, and they get close to each other. And it happens in both directions. At the front, yes, and also behind here is hidden, but you can have a hydrogen there, which is also 1, 3 away from the X group. They will see each other. They will interact, and you will end up with a problem. So groups prefer to be equatorial. How does an axial group go to become equatorial? Through the ring flip, which you know in great detail because you've been working like you've never worked before. Moving along. We proved that. This is where I want to take the class after the first exam. We can prove things without having to memorize them. You do have to know a certain amount of stuff. You need to know your pKa's. What's a pKa of a carboxylic acid? If you haven't learned your pKa's, just stay home Friday. It's not worth it. If you have, great. You'll be in great shape. What about electronegativities? What's the electronegativity of carbon? 2.5. You haven't bothered with that? Nice knowing you. But you put this stuff together, it starts to become very manageable if you keep up. We have now done what really is our second look at delta G, our second look at this Gibbs free energy equation in terms of describing equilibria. What was the other example? Where have we looked at equilibria before? Acid-base reaction, right? Acid-base reaction. So going from chapter 4 into the future chapters, this is fundamental. Understand what makes this more stable than this so that this is preferred. If this is more stable than this, you will have more of this at equilibrium. So populations become key. How much of this stuff do you have? And that might dictate what happens next. So that equation now, we've seen it twice. If you didn't get this from 1516, I think 1516 was interesting this year. And some people missed out on a bit of stuff, but hopefully we've covered it and you're now in good shape. So moving on from that. We can do this with fairly complex molecules. If you understand fundamentally that groups prefer to be equatorial at this level, then away we go. We can talk about this in the same sense we did with acid-base reactions. Is the left hand favored or the right hand favored? Even though they're fundamentally different processes. An acid-base reaction is a chemical reaction. This is not. This is essentially you sitting down and standing up. That's the only difference. You're still the same person. So be ready for K. Be ready for equilibria. Be ready for constants. Be able to answer not necessarily actual numbers, but whether it's greater than 1, less than 1, or approximately 1. That's a big, big deal going into the next few chapters. So just to show you the type of question, I always put this on there. Right? It's always on there to make sure you read it because we need it after we come back. There's very little sort of fluff on these exams. It's all stuff that you need to know to get into the next stuff. So you read the question and you read it carefully. And you know, I hopefully prepare my exams carefully enough now that they're readable. You can understand them as you go through. If you have questions on Friday, put your hand up. I'll come and talk to you. And hopefully we can do this. Now the questions usually are just in text. Right, it's all text. We're all good at texting, right? Yeah, some of us better than others. And you can see that this now is just a matter of comprehension. Read the question, go to it. Organic chemistry is very, very pictorial, if you like. It's very much a picture-driven subject. As you start to think about answering exam questions, in certain other subjects, you can write a lot of stuff and hope that the professor's not paying attention and gets bored about halfway through and just gives you the points. Doesn't work here. Okay? If you're writing an essay, more than a few words, you've missed the point completely. I just ignore it. You don't need to write essays on these questions. A picture is worth 1,000 words. Absolutely. If you can represent it with a picture, draw a picture. Number one, it's faster for you and a lot faster for me to read. And it tells me whether you know what you're doing. So this is just the same type of problem. In this case, a little bit different with a twist. I have a cis isomer that has a T-butyl and a methyl. And in this case, they both happen to be axial. And if I follow this through onto the other isomer, in which one is axial and one is equatorial, and vice versa like that, what's the difference here? What's different to the ones I just showed you? The T-butyl group is much bigger. So which will go equatorial? The T-butyl group, whether you like it or not. And the methyl group has to go where it's told. In the isomer at the top, it's fine, because if you put the T-butyl group equatorial, you can also put the methyl group equatorial. Everything's great. No issues whatsoever right there. But down at the bottom, which do you prefer, this one or this one? On the left, because the T-butyl group is equatorial, and this guy just has to go axial because that's the nature of the molecule. You can't avoid it. But it's just common sense. You want the bigger group to go equatorial, and the smaller group just has to deal with it. Other types of questions, again, just be careful. There are at least, I think there are 4 years of exams out there now, maybe 5. You need to be practicing those things, not memorizing them. Don't have the answer key next to you until you've actually done the exam, and you can then diagnose whether you know what you're doing, and then come ask questions if you're stuck. We have a system here which happens to have a similar situation, but it's changed the orientation. It's now 1-2 instead of 1-3, and things change. Don't memorize cis this is better than cis that, or trans this is better than trans that. Be able to do it from scratch. That's what you're going to be asked to do. We can see here now, again, this situation, you'd rather be there because the bigger group is equatorial. And down here, this is horrible, they're both axial. And this is much better, isn't it? Because both of them are equatorial. And again, there is no problem here. That T-butyl group and that methyl group are not close to each other, they are pointing away from each other. That's not an issue. So what we finish off with in chapter 4 is just taking this into the bigger world. When we come back after the exam next Monday, and we start doing chapter 5, which is the last of the preliminary stuff, then we get into mechanism for real. These rules are important. These rules come into play day after day. We will, and I think Tyler will corroborate this, we will talk about stuff from the first week and the last week of 3720, and all the way through. It just keeps building on itself, these basic fundamental issues. So I have a system here which just confuses people. This is something called cis-decalin. My 2 hydrogens are both wedges. That suggests a cis orientation. This is trans, this is down, this is out. If you saw something like that, the people who want to be physicians, pharmacists, engineers, clinical laboratory technicians, whatever, people who are going to do jobs that other people rely upon, and especially in a safety sort of environment, you need to be confident in what you're doing. You need to be able to put what you know into practice. So this always destroys people. But the way you look at it is, what is this? It's a cyclohexane. So guess what type of problem it is? It's a cyclohexane problem. It's amazing, isn't it? Yeah? This idea. Anybody heard of this Occam's razor idea? You heard this in philosophy? The idea that the answer is usually the simplest one. Right? It's a cyclohexane, so don't get lost. So if that's a cyclohexane, That's an R group. That's an R group. Just ignore that for the time being. And deal with it like a cyclohexane problem. We just did the cis and the trans 1,2-dimethyl cyclohexane. It's exactly the same problem. You just have to have the confidence to be able to see that and to be able to apply what you know if you know it. So we would draw here cyclohexane here. If it's the cis isomer, one hydrogen's up, the other hydrogen's up, and then I have to put the R groups in here. There's one R group, there's the other R group. If you can draw the rest of it to put a cycle in. It doesn't really matter. But that is a situation where one of the groups is axial, one of the groups is equatorial. If you go over on the other side and you draw a cyclohexane, then one hydrogen is sticking up, one hydrogen is sticking down, and then my R group is there, my R group is there. If you want to get fancy and finish it off, there's the other chair. It's just the same problem that we just dealt with. You can put whatever you want on these cyclohexanes, and it's the same issue. Okay? So there is the actual answer to that problem, which appears on a couple of old exams. Oops, and you'll find now it's the same issue. You've got axial substituents in certain places that you don't want them. This is axial, not so good. This is equatorial, and this is equatorial. In fact, both of those cycles, everything's equatorial. So that is preferred. The argument is the same. Just because it's a different looking system doesn't mean the argument changes. Jacob, you all right? Desiree? You're staying awake today, well done. Okay. Here's your world for most of you. Most of you have to deal with much bigger molecules. You can see here a couple of hormones, testosterone, estradiol. They are full of six-membered rings. You have to understand them to understand their pharmacology. A lot of you need to do that in the future. The bicyclosystems, again, these compounds have six-membered rings. We need to understand something about their shape. If they're a pharmaceutical, we can use that then to predict whether it's a good binder or a good inhibitor for a process, and we can design around that. So what we tried to do here in chapter 4 is introduce the idea of shape for real. We talk about sp3 being tetrahedral and all that stuff earlier on, but this is now putting it into practice in bigger molecules, and this is where the first exam, which comes at a really good time now, is going to test you on the fundamentals, on the basics, on the language. So be ready. We'll talk about this type of thing in the future based on what we just did, and that's pretty much it. On Friday, be here at 11, be ready to go. Bring a picture ID of yourself.